Okay, so let's get started. So my name is Pranabendu. So I'm a faculty at CMI. So I will talk about some applications or like how linear algebra concepts are used in machine learning to some extent. So today I'll talk about some very basic stuff, essentially like, so let's start with just, numbers and vectors and all these things. So in machine learning, you're sort of dealing with some data, right? Like, say you want to classify some images, right? Or you have some text and then you want to do something with that text. Maybe just identify the sentiment in the text or pull out some information contained in that text, right? So you may have some audio and then you might want to say convert that audio into text, right? So you said something to the computer, right? So nowadays like Alexa or something, it listens to your voice and then converts it into most likely a text command and then executes that command, right? So things like that, like computers are doing this commonly. And then there are more classical algorithms which deal with, let's say, for example, your bank, right, probably has lots of data about you, right? All the transactions you do or so on and so forth, right? If you have a credit card or something. So they can potentially look at a transaction and flag it as, unusual or maybe fraudulent or something. So all of this is done by computers, right? So the first thing we should ask is that how is the computer, how does the computer understand this data or process this data, right? So the data that we get from real world, it is in various formats, right? It is text, picture, video, audio, or it could be just numbers, right? So the first question would be, how does computer handle all these different types of data? So to start with, computers, as they are constructed, understand only numbers in some sense and binary numbers, right? So you cannot expect a computer to sort of understand an image directly, right? So how does it, process images? Well, so the natural thing to do is to convert it into a collection of numbers, let's say. Let's write, say, real world input. It has to be converted into some collection of numbers. So computers are very good at understanding, single numbers or so-called vectors. So I hope all of you know what vectors are. So a vector is just a sequence of numbers, right? Or matrices, which can be thought of as a sequence of vectors, right? Or you can think of it as a sort of a two-dimensional sort of sequence of numbers, right? Every position, like at ijth position, there is some specific number. So this notion can be extended to higher dimensions. So you can have these so-called tensors, right? So this is like a 3D tensor. I don't know if I drew it correctly, but you get the picture, right? So you can have 3D tensors, you can have 4D tensors, so on and so forth. So this dimension, what dimension the tensor should be. Should it be 0? Should it be 1? Should it be 2? Should it be 3, 4, 5? All these things are something that you have to decide when you go from a real world input to a collection of numbers. And this step itself is very crucial. So today I'll start by focusing on this step and then we will go on to other things. So let's start with an example. Suppose you want to process some text, right? You have, you have a book, right? Or maybe you have a very long news article or something, and you want to summarize it into a few lines, right? So the first thing to do would be to give this news article, which is a real world thing, would be to convert this into some sort of a collection of numbers, right? So my question to you is, how would you do that? There can be many ways of doing it, but, maybe you can come up with one way. Okay.
You can get a stream of numbers.
Okay, so here is one idea that, well, text input is basically a sequence of alphabets, right? Well, alphabets, numbers, punctuation symbols, and spaces. So text is basically a sequence of these things. So why don't I give each of these things some numbers, right? So let's say A becomes, or let's say for simplicity, let's say 0 becomes 0, 1 becomes 1, and so on. Then A becomes, let's say, 11. Right? The 9, no, sorry, A becomes 10. 9 became 9, right? A becomes 10, B becomes 11, C becomes 12, and so on. Yeah. Who?
Or there is no person.
What is not visible? Oh, you're online. Okay, I'll try to write in a bigger size. But you understood the idea, right? Yeah, so I was just writing down some arbitrary way of mapping these alphabets, numbers, punctuation symbols, space. No, so they cannot see the text size. Yeah.
This is not clear.
Okay. Right, so I was just saying that why don't you use why don't you just, like, here is an arbitrary way of doing this. So 0, this is even worse. So can you see the 0, people online? Hopefully they can. So I'll just map 0 to 0 for simplicity. 1 to 1, and so on. 9 will become 9. Then the alphabet A will become 10. Right? The next alphabet B will become 11, and so on. Right? So this is a way of converting text into a sequence of numbers. So what we have come up with is roughly something which would be equivalent to this so-called ASCII encoding. So this is something that people came up with way back when people started, working with computers. So they had to do this thing essentially. Right? So they came up with a standard way of encoding text into a sequence of numbers, and then the sequence of numbers were processed by computers. Right? So what would be the advantage or disadvantage of such an encoding? Okay, well, what would be the primary disadvantage of such an encoding, let's say? Can you speak up louder? B. If I want to write 11 and B as well. But 11 will be essentially written. Okay, so maybe I should clarify a bit more. So in this encoding, so as I said, computer understand binary numbers, right? So what I do is that to represent these numbers, I have a binary string of a certain length. The standard way is to keep a 8-bit binary string to represent numbers. By 8-bit, I mean that there will be 8 zeros or ones, right? And a particular sequence will represent a particular number. In some sense, well, all 8 zeros will represent 0, right? So 1 will be represented as 0, 0, 0, 0, 1, like 7 zeros and so on. 2 in this thing would be 0, 0, whatever, and then 1, 0. Right? So this is the binary encoding of these numbers. And binary encoding is something that computer understand. They don't actually even understand normal numbers. Right? And for this binary encoding, I need to keep strings of a particular length as the final way of representing numbers. So I have reserved that I will write down my text as a sequence of numbers, but each of these numbers would be written down in binary as a string of length 8. Okay. So why 8 was chosen? Because, well, actually initially 7 was chosen. 8 was chosen for some other reasons. So 7 was chosen because if you count the number of alphabets, numbers, punctuation, space, all these things, they don't add up to more than, let's say, 128. In this way of encoding text, you don't need more than these many different symbols, right? And to represent these many different numbers, which would be from 0 to 127, so this you can figure out by writing, by observing that 127 is essentially a sequence of 8 ones. Okay? I mean, this is just the base change into, binary of 127. So it is enough to have these many distinct symbols to represent text, right? And so I can represent my text as a sequence of, 8-bit length binary strings, one after another. So if I wanted to represent 11, as you said, it would be represented as, two things, this guy representing 1 and that guy representing 1. Whereas if I wanted to represent this alphabet B, it would be represented as a single bit string with the binary encoding of 11 sitting here. Right? So there is no way you will confuse this with this. Right? So everybody is clear on this? So this is essentially like at the very beginning of what you can, do with things in the machine learning setting. Even before you go to machine learning, you need a computer to do machine learning, right? So how does a computer understand your data? So this is how it starts off with. So I just want to make sure that everyone got this, right? You're not confused about anything here. And let me just point out that, okay, I'll come to the more complicated stuff later. Now, this is how I represented text. What about an image? Okay, so then so each pixel can have many different colors, right? So how will you represent that? So what is RGB? No, I know that, but I would like you to spell it out so that everyone also is on the same page. Yeah, so what is RGB? Okay, so before we start representing images, maybe we should make it a bit simpler and say we want to represent black and white images, right? If I want to represent black and white images, then it is enough to say that I'll take my image, which is, let's say, this square. I'll cut up this square into lots of tiny little squares, right? Maybe for our purposes, some 100 by 100, many different squares. And in each square, I will measure the intensity of the light, right? So if it is dark, it will get some, low value corresponding to that level. If it is bright, it will get some very high value. So this is one way of representing an image. And this image is being represented as a 100 by 100 dimensional object, right? Like a matrix of dimension 100 by 100. If you wanted to represent a color image, then people from physics have figured out that you only need 3 different values for some 3 primary colors, which are red, green, and blue. Right? So you need to keep 3 matrices. And the first matrix keeps the intensity of the red values, the second for the green values, and third for the blue values. Right? And if you compose all 3, then you get back your image, your color image. So if you actually take a magnifying glass or something and look at the laptop screen, you will find that it is actually, laptop screen is like this. Well, there are lots of pixels and each pixel actually has 3 different lights. And one is red, one is blue, and another is green. Right? So you can actually sort of zoom in and see. So this is how images are represented in computers and in basically all electronics. Okay, so we know how to represent text, we know how to represent images. Here's a simple one. What about videos? Right.
Tens of speeds.
Yes, I'll come to the tensor part later, but yes, correct. So it's a sequence of images, which means it's a sequence of matrices. So for now, if we focus on just black and white videos, then one image is a matrix. So then a video is a sequence of matrices which can be thought of as a 3D tensor. Right? So you can see that easily. So you sort of naturally get some correspondence between the data that you have and the dimension of this, mathematical object that you get. You get vectors, you get matrices, you get tensors, and so on. Right? Some of these things flow naturally, but some of these things may require further refinement. Okay, what else is there? What about audio? If you there is some microphone, maybe like the microphone here. But then what is it? How is it represented in a computer? A short answer. Or what would be the simplest way?
Frequency of flow.
There's the frequency. But the frequency won't tell you, at what point this frequency starts and what point it ends. Along with the time. So there are two different suggestions. One suggestion is that you just keep the intensity level of the sound at each point in time. So you measure it perhaps thousands of times per second. That's what actually happens. And then at each time instant, you keep the intensity of the sound level as the representation. Another suggestion has been that, what was it exactly? The frequencies and... Okay. What time, what frequency?
Amplitude also.
Yes. Yeah, so what we are suggesting is that we show a bit more detail. The frequency, the amplitude, maybe the time, and so on and so forth. So that is another representation, which is also used in, like, when you want to do something else. Essentially, the format or the way in which you show your data depends on what you're trying to do with the data. Right? So in some cases, like the simplest way that is suggested, that is what is usually done. But if you have some audio and let's say you want to, like, we have these equalizers in our phone, right? We increase the bass or decrease, things like that. So if you want to do those things, then you have to go into the representation that you were suggesting. So there are different ways of representing the same data, right? And depending on what you want to do, you have to represent your data in that format, which sort of brings into question the thing that how do you go from, this representation for sound that he suggested to the representation that you suggested. So there must be some way of converting from this to this representation that you were suggesting. So the ways of doing this is yet another aspect of, how computers handle data. But all of this goes into like all this signal processing, audio processing stuff. So I'll not really go into that direction. But I'm just saying that for the same data, there are different ways of representing it depending on the application. And it is not a simple way to convert from one format to another format. So let's look at the text thing once again, just to get a different flavor. So what you have done is that you have represented this text as a sequence of numbers, right? You are representing it as a sequence of alphabets which are encoded as numbers, right? So for simplicity, let's just think of this as a sequence of alphabets, because we know that alphabets have become numbers. Now, as I was saying, so you want to do some machine learning task like summarize the text or something. So do you think this, so let's say we do something even simpler. We just want to decide, let's say you're just given one line of text, right? And you want to decide if that line of text is a positive statement, is it a negative statement, or is it some sort of a neutral statement? Right? So this is called, like, this is a simple version of sentiment analysis. So you have the text, like it's a tweet or something, it's a short one-line text, which is given in this format, let's say. So do you think that this is a useful format, or how would you work with this?
So I have to find some specific words, the sequence of words are there in there.
Okay.
Say that it is positive statement or not.
Okay. So what you're doing is that you have represented your text as a sequence of numbers, right? Or it's a sequence of alphabets, and now you're looking for words, right? So some of the objects that you're looking for are words, but the basic building blocks of your text representation are alphabets. So do you think you should stay in the alphabet representation, or should you go into a different representation?
Try to
What you are, what you know, whether start from there. We know as a word only whether it is faster than that, so we can design. Not in the text level.
Not in the alphabet word. Yeah, so the language, generally the meaning that is encoded in language, that is represented at word level and not at alphabet level. So if you are trying to do something, especially in, say, in machine learning, with sentiment analysis or any of these things, it makes more sense to come up with a representation over words rather than over alphabets. So what would be a way of representing text over words, like as ultimately as a collection of numbers? So you want to take any dictionary, and then the first word becomes 1, the second word becomes 2, and so on. Okay. So can anyone think of any? Okay, so that is a valid representation. Now, do you think it's a good representation?
It depends on the application. We have to change our own dictionaries.
So, okay,
Start with would of text that
let me try to explain. What the issue. So as you recall, audio can be represented in one of two ways: just the intensity levels, or as a collection of frequency, time, amplitude, all these things. Right? So now, if let's say you're just trying to adjust the audio of sound, right? So then can you do this directly with this representation? You want to make the audio half of whatever it is. So the Zoom is recording this audio or whatever, right? So Zoom or somebody who is listening to it decides to reduce the volume to half of what the level is currently. So do you think you can do that with this representation? This amplitude representations? Any know? How do you do that?
just pass it.
Just divide it by half. Yes. So just divide the amplitudes by half. So not actually divided by half, but by a different number because of other people. But essentially divided by, let's say, half. And then what will happen is that the sound level will become half of what it was previously. So that is an operation that you can do on this representation. But as I was saying, right, suppose you want to increase the bass, right? You're listening to music, you want to increase the bass. Can you do that directly in this representation? Because you don't know which amplitude level corresponds to bass, like the drums or something, right? So for that, you most likely have to go into this representation via some method, but you have to go here. And at this point, you can find out the amplitude of the low frequency sounds and multiply them by, say, 2 or 10 or whatever. Right? And so the bass, the low frequency sounds will increase. So that can be done here, but not here. Well, at least not easily. Right? So if you try to directly do this here, I can't think of an easy way to do this, or even actually any way to do this, except for doing that and then converting it to that format and doing it, and then turning it back. Right. So my point is that the format of the data will make certain things easier or harder. So if I come back to the text, you have represented the text as these numbers, but the numbers are like in this dictionary order, right? And the dictionary order is not a very smart order in some sense. So the word that you have here, right? So the word at position 100, I don't know what it is. Maybe it's car. I don't know, like some position car is there. Let's say it's position 100. And then the next word in my dictionary is card. Right? That is 101. So these two words have nothing to do with each other, right? They're sort of very different things. So if you wanted to do some sentiment analysis or something, right, you cannot just look at these numbers and conclude something directly. And as in, you can memorize, which words are positive, which words are negative. So you can build a huge list of positive words to all the 100, like, I don't know, if your dictionary has some 10,000 words, maybe out of those, say, 1,000 words are positive. So 1,000 is not a very large number, but for our purpose, it's still a list of, 1,000 different things. And then there are 1,000 different negative words maybe, right? So anytime you want to classify your text as positive or negative, you look at which, if any of these 1,000 positive words occur in your text, right, in your one-line text, and then count the number of positive words there, count the number of negative words, and do something. So this is definitely a way of doing this. But it's not a very nice way of doing this. As in, if I ask you to do something else, then once again you have to build some two large dictionaries and two large lists of, say, so if I ask you to classify a line of text as happy or sad or something, then you have to once again build another list of happy words and sad words, right? Things like this. So this way of representing words as numbers is nice, but it's not very, it's not the best in some sense. So what we would like is a representation where, so there is one other thing. So as I said, to classify a sentence as positive or negative, you had to have this list of, 1,000 positive words and 1,000 negative words. Right? Now, today computers can easily handle these things, but if you didn't have a powerful computer or something, right, then for that computer, it may not be able to, memorize, or it may not be able to store these, many words, list of many words in this. Or like maybe you want to classify a given sentence across various dimensions, right? Happy, sad, positive, negative, think of any other thing, right? So then for each of those tasks, you have to store two lists of 1,000 words or something, right? So, and pretty soon that all adds up to a lot of lists of words, right? So, so this just becomes more and more inconvenient, like trying to adjust the base here. Right? So I'm just trying to think, how should I introduce the next idea? Okay, so there is one more issue with this representation, and there's a reason why I chose these two words, for example. So if you notice, these two words are only off by 1, right? This is 100, this is 101. So somehow, if you built up some sort of a machine learning algorithm, right, and that algorithm saw the word 100 or saw the word 101, which just differ by 1, it has to behave very differently for these two words, right? So if it has to classify a sentence as it is about automobiles, it's not about automobiles, right? Right? These are given any tweet, right? So it could be about cars or it could be not about cars. So then if it sees the 100th word, then it's about cars. If it sees 101st word, it's not about cars. So in some sense, the machine, if it does not explicitly store everything, then it will have difficulty. It might confuse 100 with 101. Or somebody typing might make a mistake and maybe put an extra D or something like that. Think about it this way. So my point is that this representation somehow puts very dissimilar words next to each other, right? And the algorithm cannot, take any advantage of any inherent thing in here. So this sort of a thing that you put, two words right next to each other with very little, let's say, distance between them, right? They differ by only one. So this difference of one, right? So what we would normally like is that, similar words like car, let's say, what would be another word? Truck. What would have been nice if, truck was the 101st word rather than card. Like all the words about any kind of vehicles are sort of together. And then all the word about anything, some other concept like animals are together and so on. So if our dictionaries were sort of, sorted by meaning rather than just alphabetical order, then it would have been much better for us, because then we would sort of, like the encoding that we have will sort of also encode the meaning of the words in some way. But since we do not do that, so this creates a problem for the algorithm, as in sometimes at the boundary of one concept and another it will, or sometimes when things are jumbled up, it makes mistakes essentially. It misclassifies things. It may misrepresent a car as a card or things like that. Right? Or maybe there's a typing error or whatever it is. So what we would like is to represent these words in a very different manner, right? So that meanings are captured. So here is one other representation which let me suggest to you, which is that, let's say my dictionary has, 10,000 words. So here is another stupid representation, which is that I will represent each word by a very long vector. Right? This vector will have 10,000 words, 10,000 dimension. Right? I mean, it's a list of 10,000 numbers. And in my dictionary, wherever this particular word occurs, I'm going to put a 1. Maybe for car, it's at position 100. And I'll put a 0 everywhere else. Suppose that I did this. It's a very bad representation in the sense that it uses a lot of memory, right? I have to store 10,000 numbers where most of them are 0 and only there is 1 in one place. But for now, let's just, stay with it. So if I represented things like this, then car looks like this. And this card, which is at position 101, it looks like this. Right? And this position is 0 here and this position is 0 here. So now if I take any two words, right, and I look at the distance between those two words in some sense, which is like the difference in these two vectors, right? Let's say this vector minus this vector for whatever reason. So I'll always get back a vector which has a 1 somewhere and a -1 somewhere. Right? So in some sense, the distance or the difference between the representation of two words in this new way that I suggested, it is it is not it is not pushing any two different words together. In fact, all words are sort of at the same distance from all other words. I mean, I'm not explaining this formally, but you get the idea here, right? So the way I have represented it, for each word, I have a different index in these vectors, and I have a 1 for that word only in that index. So this is also another way of representing text. The text is a sequence of words. For each word, I will get this very long vector. I'll just put these vectors next to each other to get a matrix. And that would be a representation of the text that I have. Okay, here is a question for you. So given that for every word, I mean, I have a 1 at a different index, right? So what if I take all the words in a text, right? Which will give me these different vectors, and I add up all those vectors. Then why can't that be a representation of a sentence? What is wrong with this representation?
Throw me order.
Correct. So the order also is important, right? So I cannot convert that matrix back into a single vector by adding all these things, even though it is possible technically. So if I only cared about the set of words, then that order is like that, just adding up these vectors is okay. Right? But if I cared about the sentence itself, then I have to preserve the order, and so I cannot add them up. So this classification thing that we were trying to do, right? Classify sentences positive or negative. So I think you suggested that we just look at the words in the sentence, see how many positive words are there, how many negative words are there, and then based on that we make a judgment. Right? So if this is all that we cared about, then it is actually valid to add up all the vectors in a sentence, because this adding up preserves the set of words, right? But if we wanted to do something more complicated, then this is not sufficient. Right? So everyone gets this? Okay. So before I go to the next thing, are there any questions? We actually have only 15 minutes. Okay, good. So this representation may bring very different words together and separate some very similar words. This representation keeps all words at the same distance. If you visualize this, suppose I only had 3 words, right? So because I can only draw in 3 dimensions. So then what is that representation? Then it's 3 unit vectors, right? So one is this, and one is this. And in some sense, this vector and this vector, the distance between them in 3 dimensions is the same as distance between this and this, and this and this. All vectors are at the same distance from, like any 2 vectors are at the same distance. Right? So that second representation, actually, yeah, thanks for reminding me. So this representation, what I want to say is that this representation is biased. Biased in the sense that it brings certain words together and separates out certain words. That representation is not biased. And being not biased is quite important, because algorithms sort of take the implicit bias into account. So let's look at the representation of a photograph, a black and white photograph in this form. Can you think of some, biases in this representation? Okay, let me just tell you. So if you look at this particular pixel, right? So this pixel in this matrix representation is right next to this pixel and these surrounding pixels. So another representation of this thing could have been, I'll take this pixel and somehow arbitrarily put it in the first position. Take this pixel and put it in the last position. Things like that. So there was no need for me to represent an image as a matrix where the pixel is mapped to its corresponding position in the matrix. I could put it in any arbitrary position. But that would have been stupid, because it loses some information that is already present in the input, which is that this, whatever object is there in this image or something, like, if it involves this pixel, it's likely to involve that pixel. Or like it's a composition of, nearby pixels that form objects. So this is a form of bias that is present in the representation itself. In this representation, there was some other kind of bias present, which actually is something we did not want. So when I come to this representation, at least the words themselves have no bias. But when I, let's say, put a sequence of vectors together, so because the ordering is preserved, so that gives us some bias towards, representing the sentence correctly. If I added up all these vectors, then that ordering is gone. Right? So once again, so we lose information. It's just like jumbling up the pixels. Right? So it looks like some static noise or something. So my point once again is that it is very important that we carefully think about how we represent data before we even start doing anything with the data. Right? And certain ways of representing the data is more helpful than certain other ways. Right? So for example, here, this audio thing, it was easy to change the volume here. Right? But if you wanted to increase the bass or something, suppress some frequencies, that is very difficult here. Whereas it is easy to do here. Over here, if you wanted to change the volume, it is not impossible, but it is more time consuming. Right? Because you have to reduce the volume of every single frequency thing. Whereas over there, you just divide them by half or whatever. Right? So every way of representing data has some advantages and disadvantages. And so there are multiple ways of representing data. Right? And then like you choose the correct way as per your purpose. And then you also have to figure out ways to convert from one format to another. So let me just end with the final thing about this thing. So as I said, so this is not a very efficient way of representing things. Plus, as you may have noticed that while it does not put dissimilar words together, it also does not put similar words together. So we would like some sort of representation that does that. So there is something which is called, let me just write it here, word to vec. So word to vec is a concept. It's not actually an algorithm. I mean, there are many different implementations of this. So let's just think of this as some complicated function that takes the words and maps them to some vectors in a dimension which is actually much smaller than this. Let's say the dimension would be, I don't know, 200. Okay, or something like that, not 10,000. So you map each word to some vector in some slightly high dimensional space, like 200 or 500 or something, not 10,000, such that words which are very similar, they are sort of clustered together. Right? And in fact, this word to vec was something people, this is something that people, let's say, programmatically came up with. So they trained, let's say, some neural network on a large corpus of text to map. Somehow they figured out how to map, similar words to similar vectors. And then it could show some very interesting things. Like if you look at the vector of king, this is a very standard example actually. And to this you add the vector of woman and subtract the vector of man. I think this is what it was. Now what you get is the vector of queen. And actually not exactly, but very close.
So when you say close, what is the notion of distance?
Simple L2 distance, let's say. Normal standard distance, that is. So there is some representation of words into some, let's say, 200 dimensional or 500 dimensional, I forget what, but not very large dimensional vectors, so that words are sort of clustered by meaning. And even further, you can actually, do these sort of things, that you can take a word, take the vector of a word, and then you can swap out the gender by doing some like arithmetic essentially. Right? Okay, so this is what I wanted to speak about today. So I think we have almost reached the end. So I would rather answer some questions. Yeah. So this 10,000 length vectors, right? You're talking about these 10,000 length vectors. So think of, okay, here is a sentence I use. Let's say you have two sentences. So let's say the first sentence is I am Ram, not give me a second name. Sita. Okay. And another sentence is I am Sita, not round. So if you look at the vectors of these words, right? If you have if you represent them as matrices by stacking the vectors, they will be different matrices. But if you add up the vectors, you'll get the same vector, right? So this addition, if somebody then asks you, who is the person speaking? Is it Ram or Sita? You will not be able to answer. So this is a simple example of why that adding up thing is not a good idea. If you take a weighted sum, what would be the weights? So the problem with that would be, so there are many problems. So one problem would be that suppose this sentence occurs, maybe at the end of a longer sentence or the start of a longer sentence, right? So depending on the position of this sentence in a longer sentence, the vector you will get for this particular sentence would be very different. So your algorithm will have a difficult time dealing with all these different scenarios, which correspond to the same thing. Okay, so that's one of the problems with this way of doing it. Any other questions? Okay, so then let me tell you one more interesting thing. So here, when you represented text as a sequence of alphabets, blah, 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 then each of these numbers that you had, right, each number corresponding to an alphabet was a fixed length binary string, right, 8-bit. But turns out that if you're interested in, say, compressing the data and using less space for the text, then this is not the best thing to do. And if you start off with some text, then the highest number of, the highest number of occurrences is likely to be space, right? So it is not a good idea to use, 8 bits for representing space. Maybe you should use fewer bits, right? Whereas some very obscure alphabet, let's say some very obscure punctuation mark, I don't know. I think this is fairly obscure. We use it a lot in math, but maybe English major is unlikely to use this tilde symbol. So this, you can probably give it even, double, 16 bits. So there is an encoding of text, or rather alphabets, based on their frequencies in a given text, right? Which will use overall fewer bits as compared to this. So the number of bits used by this thing would be 8 times the number of, the length of this text in alphabets, right? If there are 10,000, alphabets, blah, blah, blah in a text, then it would be 8,000 bits. Whereas that other representation, which uses smaller length sequences for more frequent things and longer length sequences for less frequent things, that would end up using maybe only 4,000 bits overall. Right? So this is known as this Huffman encoding. Hopefully I'm spelling this right. So if you're interested, you can look this up. Yeah.
What the length of the block when you're reading?
That's the point, right? So that's why this is a cleverer encoding. So here I always know that it should be 8 bits, so I can read the next 8 bits and next 8 bits. But when you use variable length strings for different alphabets, then somehow your string itself has to have some property by which you can identify when it begins and when it ends. So look up Huffman encoding and you'll realize, so what happens. So
Rule later can be a substring.
Essentially, yes. So you have to ensure this, and then there is a very simple algorithm to do this as well. So that is what this is. And I think this is also optimal as far as this type of compression is concerned.